Okay, right. We are still on the topic of high voltage, and the thing that we are now going to talk about is Townsend second ionization coefficient. Okay, right. So let's go. From the equation, obviously there's an equation here. Okay, at a later stage we'll start talking about equations. For now, let's just first touch on the theory. We need to become theoretically comfortable with the subject that we are touching on. So yeah, so let's go. We have taking log on both the sides. This is now if you apply log. Okay, right, on both the sides. Why do you apply logs or the natural logarithm? It's basically because there's an exponential function involved. So yeah, we're not going to touch on mathematics now. So yeah, so it's not like I don't know the mathematics. We will touch on that. So yeah, but anyways, this is a straight line equation with slope alpha and intercept natural log I subscript 0 as shown in figure 1.3. Now, if we look at figure 1.3, we'll notice here they talk about the variation of gap current with electrode spacing in uniform E. And then they give another mathematical expression. So yeah, scary stuff. As shown in figure 1.3, if for a given pressure P, E is kept constant. Okay. Now, when we started this, if you just slightly go back to the introduction, at the introduction, what did we talk about? We spoke of normal pressure, normal temperature. Now, somewhere along the line, now they talk about for a given pressure, meaning there's now a variation. Pressure is now being dictated. Okay, so there's a change that is happening somewhere along the line. Okay, and then obviously if you keep some things the same so that you can change others, meaning with a change some of the stuff they have to be kept constant, and in this case what is kept constant? It's our E. Obviously I don't know what E is. We are going to figure that out together. Right, so let's continue reading. Townsend, in his earlier investigations, he had observed that the current in your parallel plate gap increased more rapidly with increase in voltage as compared to the one given by the above equation. To explain this departure from linearity, okay, Townsend suggested. Now, obviously, I have to explain because that's what this whole excursion is about. Yeah. Here it says, to explain this departure from linearity. Linearity, the word that we used was the word proportion, in proportion, meaning proportionality. And that happened up until what? I subscript 0. Okay? I subscript 0, once you've reached the point, your current or your saturation current, I subscript 0, what then happened was we then reached saturation, meaning a flat line, otherwise known as a plateau, up until you reach a given voltage. Then from that voltage, your current will then increase at an exponential, not exponential rate, but in an exponential quantity. Okay, for now, let's say that. However, in the beginning, there was a sense of proportionality, a sense of linearity. Okay, now, here it says, to explain this departure from linearity, Townsend suggested that a second mechanism must be affecting the current. He postulated that the additional current must be due to the presence of positive ions and the photons. Okay, the positive ions will liberate electrons by collision. The positive ions, they will liberate electrons by collision with gas molecules, okay, and by bombardment against the cathode. Similarly, the photons will also release electrons after collision with gas molecules and from the cathode after photon impact. Obviously, I have no idea what he's saying here, but we'll read it again, and then at a later stage we will draw pictures if we have to, just so that we can properly understand this. But for now, we need to cover the theory, simply meaning we should have at least have read through everything or most of what's happening here, so that when we refer, then we refer to something we've already done. So let's reread it. Townsend, in his earlier investigation, had observed that the current in parallel plate gap increased. Okay, that the current in the parallel plate gap, it increased more rapidly with an increase in voltage as compared to the one given by the above equation. Okay, to explain this departure from linearity, Townsend suggested that a second mechanism must be affecting the current. He postulated that the additional current, okay, must be due to the presence of positive ions. Positive ion, it just means particles that are positively charged. Okay, so he is saying the additional current must be due to the presence of charged particles that are positive, as well as the photons. Okay, the positive ions, meaning the positive charged particles, they will liberate electrons. Okay, they will liberate electrons by collision, meaning they will help set electrons free by collision with gas molecules. So your positive ions are in collision with your gas molecules, and in the process, what gets done? Electrons are liberated, okay? As well as by the bombardment against the cathode. So you have your positive ions, they are colliding with your gas molecules, and then in addition to that, they are bombarding against the cathode. And then that sense of bombardment against your cathode, it does what? It liberates the electrons. So we can assume that your liberated electrons are liberated from your cathode through this bombardment or the sense of collision. Okay, right. Similarly, the photons will also release electrons after collision with gas molecules and from the cathode after photon impact. Similarly, that already tells us everything. Okay, meaning in a like mannered way, the photons will also release electrons from where? From the cathode, obviously. After what? After collision with gas molecules. So your photons, they will collide with your gas molecules, and yeah, electrons will be released from the cathode after photon impact. So the moment there's impact, simply meaning there's a collision of your photons hitting your cathode, what is going to happen? Electrons will be released. Electrons will also be released when you have your photons having impact with your gas molecules. That is essentially what this is saying. Obviously, I don't see how that is true, but what I think, feel, and say is it's irrelevant. Yeah, so here goes. Let us consider the phenomenon of self-sustained discharge, where the electrons are released from the cathode by positive ion bombardment. That is what we call self-sustained discharge. Discharge, it simply means charge being released. In this case, electrons being released from your cathode. We call that what? Discharge. And in this case, we are talking about a phenomenon otherwise known as self-sustained discharge, and that just means electrons are released from the cathode by positive ion bombardment. It's being bombarded by what? Positive ions. In this case, we can assume it to be what? Positively charged particles. In this case, it's also true if those, I'm not going to say if those particles are photons, but I will say this is also true in the case of photons. Okay, right. Now, let n subscript 0 be the number of electrons released from the cathode by ultraviolet radiation. So you are beaming it or subjecting it to ultraviolet radiation, and then guess what? A number of electrons are released, and this number of electrons, we will refer to that as n subscript 0. Okay, where n subscript positive is the number of electrons released from the cathode due to positive ion bombardment, and n the number of electrons reaching the anode. Simply meaning, yes, electrons will be released, but some of these electrons moving perpendicular to your field, they will eventually reach the anode, and then these electrons, we refer to them as n. Okay, now let V, known as your Townsend second ionization coefficient, okay, be defined as the number of electrons released from cathode per incident positive ion. Then you have this little formula here. Okay, right. Now, the total number of electrons released from the cathode is n subscript 0 plus n subscript positive, and those reaching the anode are n. Therefore, the number of electrons released from the gas equals n, meaning the number reaching the anode minus open brackets n subscript 0 plus n subscript positive, and corresponding to each electron released from the gas, there will be one positive ion, and assuming each positive ion releases V. Ooh, what is V? It's the Townsend second ionization coefficient. Assuming each positive ion releases V effective electrons from the cathode, then you have this mathematical whatever this is. Okay, right. However, luckily for us, that is not of significance right now. So yeah, headache over. Where B represents the number of ion pairs produced by positive ion traveling 1 centimeter path in the direction of the field, Townsend's original suggestion that the positive ions, after collision with gas molecule, releases electron, it does not hold good, as ions rapidly lose energy in elastic collision and ordinarily are unable to gain sufficient energy from the electric field to cause ionization on collision with gas molecules or atoms. Ooh, something powerful was just said. I hope we didn't miss it. I hope we didn't miss it. Townsend's original suggestion that the positive ions, after collision with gas molecules, release electron does not hold good, as ions rapidly lose energy in elastic collision and ordinarily are unable to gain sufficient energy from the electric field to cause ionization on collision with gas molecules or atoms. In practice, positive ions, photons, as well as metastables, all the three may participate in the process of ionization. It depends upon the experimental condition. There may be more than one mechanism producing secondary ionization in the discharge gap, and therefore it is customary to express the net secondary ionization effect by a single coefficient V and represent the current by the above equation, keeping in mind that V may represent one or more of the several possible mechanisms. So V can equate into V1 plus V2 plus whatever that is, okay? It is to be noted that the value of V depends upon the work function of the material. Whoa, work function of the material. Obviously, it's going to be dependent because your work function is dependent upon the type of material. So it is noted that the value of V depends on the work function as well as your work function being dependent on the type of material. That's what we discussed earlier, okay? If the work function of the cathode surface is low, under the same yeah, where were we? Or produce also, the value of V is relatively small at low value of E divided by P and will increase with increase in E divided by P. This is because at higher values of E divided by P, there will be more number of positive ions and photons of sufficiently large energy to cause ionization upon impact on the cathode surface. It is to be noted that the influence of V on breakdown mechanism is restricted to Townsend's breakdown mechanism, an example being to low pressure breakdowns only. Okay, earlier on we did touch on pressure. What did they say? Pressure is normal. Now here they tell us that what? It is what? Restricted to Townsend's breakdown mechanism. And then Townsend's breakdown mechanism, it means to low pressure breakdowns only. Okay, right. So at the same time, we are going to stop here, and then for the next topic, we'll talk about Townsend breakdown mechanism.